Hello and welcome to my presentation, and thank you for your interest. I'm Ulrich Viereck, and my collaborators are Robert Platt at Northeastern University and Kate Saenko at Boston University. I'm presenting our work, Learning Visual Servo Policies via Planar Cloning. Our problem setting is to learn a pixel-to-talk controller for manipulation. We want to learn a control policy for achieving a desired hand pose with respect to novel objects in the environment. We focus on the free space motion without contact. Examples are policies for mating a cap on a bottle or inserting a peg into a hole. How can we learn such a control policy? Deep reinforcement learning is less sample efficient and slower to train than supervised learning due to sparse and high variance rewards. The idea is to use behavior cloning, a form of supervised learning. We estimate the Q values using a full-state motion planner in simulation, clone the Q values to the observation space, in our case depth images, which allows us to execute on the robot without full state access. We propose penalized Q cloning, or short PQC. We assume having a planner with full state access that generates plans, in our case collision-free trajectories to the goal. We roll out the planner to generate a labeled dataset of observations, actions, and Q values. Then we clone these to a Q function. PQC combines and improves upon existing cloning methods and has the following characteristics. First, it learns a value function instead of a policy, using supervised targets, similar to aggregate. Learning Q values allows fine-tuning using temporal difference learning to improve beyond a suboptimal planner. Second, PQC incorporates a penalty for suboptimal actions, similar to DQFT. This has the advantage that resulting policy imitates the expert better. And finally, we augment the dataset with Q values for all possible actions in each state, not just for the action taken. This has the benefit that Q values of non-expert actions are learned better. We train PQC and all baselines on 500 random scenes with 100 rollouts per scene. Success is defined as reaching the goal without collision or timeout. Costs is a function of distance moved, distance to obstacles, and collision. We train for peg insertion and block stacking tasks. In simulation, we compare the success rates for the block stacking of variations of PQC, ablations, and baselines. For batch PQC, we first generate a dataset by rolling out the expert, then we batch train. For online PQC, we interleave expert rollouts, on-policy rollouts, and training. We do this for all other methods, except for DQN on-policy. On the top right shows the success on the training set over training iterations, and the bottom shows success on a holdout test set. Although the success on the training set is similar to some baselines, PQC outperforms on the test set, which justifies our design choices. The result for the peg insertion task are similar. On the robot, we run proof of concept trials. We evaluate the batch PQC on 5 different scenes, one shown on the right. Depth images are transformed by a pix-to-pix scan to appear simulated. The average success rate is about 87%. In conclusion, PQC clones Q values generated by a planner with full state access to a policy that can be executed by the robot. The main design choices are to learn Q values that can be tuned using TD learning, penalize suboptimal actions, and to learn Q values for all actions. Finally, we show that PQC outperforms all ablation and baselines on 2 different tasks. Thank you for your interest.